Today's topic is evaluating limits by hand. So this is our third evaluating limits notes. So if you remember, we started off with 9.3 where we evaluated limits graphically. So we looked at where the function was approaches, what y values the function was approaching from both sides. And then we did the same thing with the table. So instead of having the picture and tracking the y values on the graph, we track the y values through the table. And now we're going to do it algebraically, which means we're not going to look at the picture, we're not going to look at the graph, nor are we going to look at the table. We're going to do it all with algebra. So our goal today, by the end of this, we should be able to evaluate a limit algebraically, or in other words, by hand is another way we'd say that. Okay, so we start off, evaluate the following limits by hand. Evaluate the limit as x approaches 0 of this function. So graphically, we could grab our calc and graph this and then see where it approaches, or look at the table, but it's a lot quicker to do it algebraically. So the first most simple method is called direct substitution. That's where we take the value that we're approaching. So x is approaching 0. I'm going to try. As x approaches 0, we're going to take that thing and we're going to sub it in for all the x's. Now, there might be multiple x's on the top, or there might be multiple x's on the bottom, but this is the best, quickest way to evaluate a limit. So if we can take 0, we can plug it in. 3 times 0 is 0 squared is 0 to the minus 5. 0 minus 5 is negative 5. Negative 5 divided by negative 5 is 1. So like I said, this method is called direct substitution. Now, direct substitution is what I would recommend doing every single time because it's the quickest, most efficient way to evaluate a limit. The problem is direct substitution only works if you're evaluating a limit at an x value where the function is continuous. So I know that my function is continuous because when I plugged in this value, I got an answer. Okay, so let's look at what happens when we try to direct substitute and we run into a problem. So let's direct substitute into the numerator first. So negative 3 squared is 9. Plug in negative 3 here. The negative 9 take plus negative 3 is 6. 6 take away 6 is 0. Divided by negative 3 plus 3 is 0. Now we have a situation, because when we direct substitute, we get a 0 on the bottom, which is really bad news, but we also get a 0 on the top, which isn't as bad of a scenario. This is, first of all, what we call an, let me get a brighter color so it'll stick out. This is what we call an indeterminate I missed the R there. Indeterminate form. An indeterminate form means that we can't evaluate it, but it still gives us a hint. And the hint here is that whenever you get a 0 on the top and a 0 on the bottom, that means that whatever's causing the 0 on the top is the same thing that's causing, whatever x value is causing the 0 on the top is the same x value causing the 0 on the bottom, which means that we can eliminate that problem, which means that we have something on the top and on the bottom that cancels, which creates a hole. So this is a throwback to our rational function graphing back first semester. You remember at the end of Unit 2? So we had these functions that we factor the top and factor the bottom, and anything on the top that canceled with anything on the bottom created a hole. It didn't create an asymptote. That was stuff on the bottom that didn't cancel. It didn't create a 0 because that's when you have a 0 on the top that doesn't cancel. It's when something on the top and something on the bottom does cancel. So when I get an indeterminate form by direct substitution, I right away know that this function has to have a hole, which means something has to cancel on the top and on the bottom. Well, as I look at the bottom, there's not really a whole heck of a lot we can do with the denominator, but there is something we can do with the numerator. hopefully your brain said that we could factor it. So I'm going to factor this into x plus 3 and x minus 2 divided by x plus 3. Lo and behold, what do you notice? X plus 3 divided by x plus 3 cancels. So now we've eliminated the whole. So the graph of x minus 2 and the graph of x squared plus x minus 6 over x plus 3 looks exactly the same. The only difference is that one of them has a hole and one of them doesn't. So I would now be able to take my x equals negative 3, and now I can direct substitute that in for x. So negative 3 take away 2 ends up being negative 5. Let me show you graphically what I was just talking about. You don't have to do this. You can just kind of watch mine. So I'm going to graph. Remember that oscillating function from last unit? So I'm going to graph, first of all, the equation x squared plus x minus 6 over x plus 3. Oops, I'm going to do a zoom 6. See what our window, yeah, that's a pretty good window. So it looks like this thing, surprisingly, this x squared graph makes a line. This x squared equation actually makes a line. Watch what happens when I trace to negative 3. Nope, there's no y value. If I trace to negative 3.01, there's something there. At negative 2.999, there's something there. But at negative 3 itself, it's not there. Now watch what happens when I graph the equation x minus 2. So in other words, I'm going to eliminate the whole. So I'm going to turn off that graph so you know that it's not still graphing that anymore. And I'm going to turn on x minus 2. Look at this graph. It's the exact same thing. If you don't remember, here, I'll turn on the old one. I'll go back and turn this graph on. So now it's going to graph both of these. It doesn't look any different because the second function is exactly the same as the first function except for one place. I'm going to trace. Now notice this says y1, so that means this is the original equation. So this is the graph that I'm on right now. I'm going to trace to negative 3. Nothing there. When I push up, it jumps to the second equation. Now it's on the second equation. I'm going to trace to negative 3, and it's now filled in as that answer of negative 5. So what we do when we evaluate a limit algebraically, when we eliminate the whole, basically we turn our function into a new graph that's going to look exactly the same, and it's not going to have the problem that the original equation had. So there's sort of the long-winded version of why the indeterminate form is such a helpful form. So let's take a look at another one here. So now I'm going to take 2. Always, always, always try to direct substitute first. It's going to save you so much time when it does work. When it doesn't work, it's kind of a pain, but at least it gives you a hint on what kind of result you can get. So I'm going to direct substitute 2. That's 4. That's 20. 20 take away 8 is 12. 2, that's negative 12. 12 minus 12 is 0. Plug that in the bottom, I get 0 over 0 again. That's the indeterminate form, which gives me the hint that somewhere on this graph, there's a hole, and I have to figure out where that hole is. I'm going to encourage you to pause here. I'm going to have you try to factor that numerator. Got a little lazy. I should be writing the limit in front of these. Until I can direct substitute, I should be writing the limit in front of these. Kind of lazy there, Stuck. Jeez. Okay, let's see how you did factoring. So this would be an x factoring. What color? Would go with an orange, maybe a nice dark blue. Oh, how about a purple? So I would x factor this. On the top, I would have negative 40. On the bottom, I would have negative 6. That's 4 and 10. I need it to be a negative 6, so that's a negative 10. So this now factors into the 5's got to stay as a 5. Then it's got to build the 10, so that's minus 2. And then I need the 4 to be a positive, so that's got to be another minus 2. Remember, once you factor, you can quickly check to see if you did it right by doing 5x times x is 5x squared. That's minus 4. Sorry, minus 10 minus 2, which is wrong. Oh, yeah, there we go. This needs to be a 4. See, it's worth it to check. 5x, that's 5x squared. That's minus 10, that's minus 4. Minus 10 minus 4 is my minus 6. Negative 4 and negative 2 make a... Dang it, it's still wrong. I need a negative 10 and a positive 4. Good Lord. It's been a long time since I factored, I guess, huh? But that's why you check. So 5 times 1 is 5. Then I would do, so that made the 5. Then I got negative 10 plus 4. Negative 10 plus 4 is negative 6. 4 and negative 2 is negative 8. Oh, geez. Okay, well, we got there. Our checks and balances worked out. So now I can cancel the whole, and now I can direct substitute that value in. So 5 times 2 is 10, plus 4 is 14. What do you think? That's now, from here on out, you've got the basic idea. We're just going to talk about algebraic tricks that help us factor so that we can cancel stuff out. So the next one down, we're going to evaluate the limit as x approaches 3. Try to direct substitute first and hope against hope that we have something that cancels. Sorry, so hope against hope that we can just direct substitute and get the right answer. So I put 3 in there. That's going to give me 27 minus 27. Hey boy, that's 27. That's 9 times, that's 27 again. So 27 minus 27 is gone. Then that's a negative 3 plus 3, so that's 0 again. So 0 over 0 means I have a hole somewhere. Now I got to figure out where that hole is. So this is a difference of perfect cubes. So we'll use our difference of perfect cubes factoring here. If you haven't seen that in a while, there's that poster in my room that you might want to look at. You probably have this on your unit circle somewhere. If not, you're going to want to add it. This would be something I don't think I would overemphasize memorizing. We don't use it all that whole heck of a lot. And plus, I've got that poster in my room. You can look things up. So the first thing we have to figure out is who is getting cubed. So this is x is what's getting cubed minus, and then 3 is what's getting cubed. You have to first figure out who is getting cubed in each scenario. And then it's a minus b times the quantity a squared. These always switch signs. You multiply these together. So that's 3x, and then you square the last one. So that's plus 9. Over x minus, look at the bottom. I was hoping this would just be a nice factoring, but anytime you see 4 pieces, man, what does your math voice say? Factor. How would you factor 4 pieces? Factor by parts. Factor by parts. So that's where I look at these 2 parts, and I factor them individually. So what do these 2 things have in common? These both have an x, so I'm going to take out an x. That leaves behind x squared minus 3. This piece must come out. That's why I drew the brackets the way that I did. Whatever that sign is, you're taking out a negative, whatever that is. What does x and 3 have in common? The most they have in common is a 1. So that leaves behind a positive. Whoa. I'm going back here. I should have taken out an x squared. Boy, these notes are a disaster. Minus 3. Remember, these 2 groups are the same, so that becomes what we factor out. Once those are gone, what's left behind is our other factor. Anything cancel? Yippers. That's the whole thing. That's the whole reason that indeterminate form thing is so helpful. Now I can direct substitute. I can now plug 3 in everywhere. So that's 9 plus, that's another 9 plus another 9. That's 27 over 9, take away 1 is 8. So 27 over 8 would be my limit. Let's have you try the next one. Pause, give it a whirl. All right, let's see how you did. So I'm looking first at how to factor this. The limit as x approaches. No, I'm not. I'm direct substituting first. Save yourself some time. So when I direct substitute, 4 cubed is 64 minus 64. That usually means, now what does it mean if you get, let's say, a 0 on the top and something else on the bottom? Well, that's a number, right? 0 over 7 is the number 0. That's your limit. Game over. You direct substituted properly. There you go. Well, what happens if you get a number on the top, but then a 0 on the bottom? Well, what's something divided by 0? Does not exist. So then your limit does not exist. So direct substitution, even though it seems like you waste your time, it does tell you a lot of information about your function. So this is 64 times 2, which is 128. Oh boy, I need a calc for this one. 2 times 4 to the third minus 8 times 4 squared plus 7 times 4, subtract 28. Yep, 0. Okay, so we got a hole again. We got a hole. We just got to find it. So if you haven't, pause and try to factor. So this is x cubed minus 4 cubed. That's going to give me an x minus 4, x squared plus 4x plus 16 over. This is a factor by parts. So these have a 2x squared in common plus a 7x minus 4. So that leaves me with an x minus 4 times a 2x squared plus 7. Which I can now get rid of these two. 4 in there, that's 16 plus 16 plus 16, 48. 4 in there, that's 16, that's 32. Plus 7, 39. Can they reduce? Well, 2 is not going to work. Does 3? Yeah, 3 works, right? 3 goes into here once. 16 times. 3 goes into there once. And so 13. 16 over 13. 13's prime, so the game is over. Game is over. All right, I'm going to encourage you to pause again. You should be able to do. Now look, this is a plus here. So that just makes that this formula is going to be similar. Except there's going to be a plus there and a minus there. And then this is always positive at the end because you're squaring. This thing right here, the x squared, and the last term are always positive because you're squaring those things. So this would be a plus now, and that would be a minus. So give it a try. Okay, hopefully you did direct substitution first. If you did, you're already done. I don't know how many of you actually tried it, but direct substitution, when I put 2 in here, that's 8. 8 plus 8 is 16. When I put 2 in here, that's 8. That's 4, that's 8, that's 16, that's 20 minus 20. So 16 take away 40 is negative 24, which reduces to be negative 2/3. So I'm going to show you how to do it the long way just to see if you factored that. I want to practice factoring that sum of perfect cubes. But remember, direct substitution is the best way. The game's over if you direct substitute and get something other than 0 over 0. Okay, so this is going to be the limit as x approaches 2 of x plus, so this is x cubed plus 2 cubed. That's x plus 2. X squared minus 2x plus 4 over, factor by parts. This has an x squared, which leaves behind x plus 3 minus a 10. X plus, try again, x plus 2. Man, I hope you guys don't judge me by this video. X plus 2, x plus 2, x squared minus 10. Cancel, cancel, direct substitute. 2 is 4, take away 4, so it's 4. Oh, yeah, that's okay. 4 take away 10 is negative 6. Reduce, negative 2 thirds. Sorry. But direct substitution saves you a lot of time. If you can just direct substitute, game is over if it works. All right, now this one's kind of sneaky. This is where we have to kill off the root. We're going to hit this again. I'm not going to put too much into this one. That's why I'm only going to show one example. We're going to hit this again tomorrow or next time when we do the derivative by definition. So I want to kill off this root. Now, unfortunately, you can't just square something. You can't just square the bottom and the top of a fraction. Oops, sorry. Direct substitute first. So 5 plus 4 is 9. Square root of 9 is 3. 3 minus 3 is 0. 5 minus 5 is 0. So we have a hole somewhere. We just got to find where that hole is. What I'm going to do, I'm going to try to square this thing without squaring it. So think back to your... we've done this a ton this year. When we want to square something without using squared, what do we multiply by? Hopefully, your math voice said multiply by the conjugate. So what's going to happen here, when I multiply this by the conjugate, it's going to square everything without using squared. So those roots should cancel out. Now look, whatever you do to the top, you don't have a choice. You have to do that same thing to the bottom. Okay, so let's distribute this now. The limit as x approaches 5, root x plus 4 times root x plus 4 is x plus 4. Now remember how this kind of distribution is so nice when it comes to conjugates. So we did root x plus 4, root x plus 4. That's going to square it. In other words, it's going to get rid of the root. Then I'm going to have this mess, positive 3 nasty root. But then the next thing I would distribute is negative 3 nasty root. So those two things, I'm going to put little x's on them. Those two things would cancel each other out, those two distributions. But I still have to do negative 3 times 3, which would give me a negative 9. Over, now look, the numerator is a lot better. The denominator is not. The denominator is a mess. So we've got this quantity, x minus 5, times this quantity, square root x plus 4 plus 3. But life is actually a lot better than it looks, because what's x plus 4 minus 9 combined like terms? This ends up being x minus 5. If that's x minus 5, I can now cancel. And I can now direct substitute because this minus 5 in the denominator got canceled out. So what happened to the numerator? What's left up top? Well, that's still a 1. Over, now I can put the 5 in there. 5 plus 4 is 9. Square root of 9 is 3. 3 plus 3 is 6. That one's fairly tough. Like I said, we're going to hit it again when we do the derivative by definition. But I would encourage you, when you get to the homework, don't wimp out on those. Dig in. You guys can figure them out. You're the smartest pre-calc kids I know. Good luck.